Hello, everybody. Welcome to Quarkus Insights 141, where we're going to be talking about Pulsar. I'm very interested to hear about, because true confession, it's not something I know very much about at all. So let's, and Max is on the move. So
I'll be there in a second.
With some quick introductions, so we won't ask Max for an introduction because he's going to chase a horse out of his office or something like that. So how about you? Do you want to start, Matteo?
Sure. My name is Matteo Merli. I'm the CTO in Stream Native, and I'm the PMC chair and a co-creator of Apache Pulsar. Back in the day in Yahoo, it's been 7 years in Yahoo, and we created Pulsar and we open sourced it, and then we started companies around commercialization of Pulsar and services around Pulsar.
Cool. And
that's my short story.
Thank you. So how about you, Ozan?
Yeah, my name is Ozan. I'm working at the Quarkus team, everything around messaging. And I recently worked on the Pulsar integration, so I'll be happy to share our experience with it.
Cool. And Clement?
Hello, so I'm Clement. I've founded the messaging effort around Quarkus with reactive messaging and plenty of other technologies. Now I've delegated that to Ozan, but I'm still around and I'm still trying to see where we are going in the future to go with what I call modern data streaming. So that's more for a 2024 insights, not this year.
Not yet, no. Okay. So I guess maybe we could start with
we have Max.
Yes, we have Max.
Yeah.
Yes, he got rid of the horse. So maybe we could start with an introduction for those of us like me who don't entirely know what Pulsar is. Maybe I guess you probably know best, Matteo.
Okay. So Pulsar essentially is a distributed messaging and streaming platform. By messaging and streaming platform, we typically mean that we support PubSub semantics, PubSub interfaces, and kind of cater to different set of use cases around the pure like microservices PubSub models that was typically found in things like JMS and all these implementations and things like RabbitMQ, ActiveMQ, and all these other traditional PubSub. At the same time, we also support the streaming model where things like Kafka, Kinesis, and others are playing. Essentially, one of the big difference between all the systems is that we support both of these paradigms, and that means that you can use Pulsar as a single platform for both your online or kind of like OLTP workloads, where you have your microservices that are generating events, as well as your analytical workloads where you are processing and doing analytics on things that have already happened. There are several other differences around architecture, design goals, and things that stemmed around the years. But just to call out a couple of differences between all the systems is that Pulsar has been designed from the ground up to be multi-tenant. That means that you typically deploy one single instance of Pulsar instead of having one per each of your use case, like we typically people will do with Rabbit or Kafka. Therefore, you can have a single instance for a company, for an organization, and have multiple teams, multiple applications using the same cluster. That helps a lot in terms of making it easy to share data across different teams, which is one of the purposes of messaging, right? And also easy with operations, so it becomes much easier to operate a single cluster. I mean, I could go on for hours and hours. I just keep it short for now.
That's perfect. Thank you. Yeah, I think that helps position it against the sort of, the Kafka conversation and the MQ conversation. Thank you.
So
Maybe a quick add up there. I've been hearing that Pulsar is more cloud native. Maybe you can add more into that aspect.
Sure. So this comes from architecture of the software, right? So if you look at things like, in the traditional messaging systems, typically they're really not horizontally scalable, like things like RabbitMQ and so on. They were designed to be like a single server, or they have a different models of replications, but they were not horizontally scalable. Kafka, on the other hand, is scalable, but there is one thing that Kafka does in our does not very well, which is that it ties the data of one partition to one single server. That's because basically the broker that's the leader, and then there are followers, but essentially that these three nodes will have the entire data for the partition. Now that means that you cannot just add new servers. You can just automatically scale up or down because the data is there. And if you just like add more servers, like increase your set of pods, well, these pods will not have the data, so they will not have any traffic. You have to do a cluster rebalancing protocol, mechanism that in Kafka, but that means that you have to copy a whole bunch of data. So if you want to expand capacity, then it's very hard to do. It's not just hard; is that it is something that takes a huge amount of impact on the cluster. And if you are already at capacity, then means that you are in a bit of trouble. In Pulsar, by the main difference architecture is that we have two layers in the system. We have brokers which are stateless, or better said, they have no durable state. There is state, but is transit state. So basically, a topic is assigned to one broker at a given point in time, but that ownership can very quickly change without any copying any data. And then we have bookkeeper and bookies, which are the storage layer. Now the data is segmented also over time. That means that the data for one single partition can be spread across the entire set of storage nodes. Therefore, we can add storage node as we please, and we can add broker as we please, because we can scale up because we can easily move topics from one broker to another because we don't have to copy data. So basically, everything becomes elastic at that point. You can scale the broker layer, scale the storage layer without any major pain.
So is that the main thing, the difference between Pulsar and Kafka? So it sounds like you're saying that, hey, you can use Pulsar as a way to data, but also have the streaming. But then it sounds like you can get that in many places where the thing that Pulsar does differently is basically the architecture for scale. Is that right? Like I'm very new to Pulsar. So.
Also like if you see, no. So if you see Kafka as well, like the way that the place that Kafka comes from is from analyzing logs, right? The original use case for Kafka was taking HTTP logs and have a way to get them into HDFS. That was the first use case for Kafka. And therefore, there's this concept of that Kafka is a distributed log, essentially, right? Now, that's a powerful abstraction for a storage system. But if you look at application developers, they don't reason in their use cases as a log abstraction. They typically use something more high level. Like PubSub is much more abstract, right? There's no concept of log. Now you can see the log as an implementation detail. Underneath, right? A segmented log. The point there is that from a user perspective, they don't reason in terms of I have my data in a log. Instead, it's more like I want to connect different services and I want them in the easiest way possible. And also, I have various different complex ways of routing and consuming the data. That can mean that I can maybe use a worker queue model, or I might need some things like delayed delivery. I want to keep track of messaging individually, like consuming out of order, because maybe I have a thread pool underneath, and then I don't want to keep track of all the acknowledgements, and on and on. Right? So there's a bunch of features and a bunch of things that are more high level that Kafka does not have.
Maybe I can add to that. Writing the integration, I mean the connector for the reactive messaging, I was pleasantly surprised that most of the things that we were trying to add to the Kafka as a feature, the Kafka connector as a feature, were already inside the Pulsar clients. So it was, of course, an effort to be able to understand how the features work. But let's say the delayed retry or the dead letter queue, or even the retry of the individual messages were already there inside the client. Whereas those are the things that we added on top of the Kafka client in our Kafka support. I think Spring does that also in different ways. But what Pulsar client, at least in the client side, gets is those are the most common use cases. Again, like different topologies for consumer and producers. And the like dead letter queue retries, non-blocking retries, etc. Or like, and we didn't mention, but there's also the schema registry support, which comes built in with Pulsar.
That's really nice.
Yeah. So and as you say, you can implement those features on top, maybe on Kafka. They're not trivial. I can assure you that. I mean, and you guys can do it. But like if you look at the average developer that is trying to build an application, and he has to build all these things on top just to make some very common functionality, then it's a lot of work, and it's a lot of like non-trivial work there to implement for these developers.
Yeah.
So we've got a question already, but it's not about the sort of the general architectural considerations for Pulsar. Someone's getting excited about the demo.
We only have Kafka at the moment in this repository, but
I think so.
Yeah, but let us add Pulsar as well tomorrow, let's say, because it's a bit later. Or if Matteo wants to contribute, but yeah, it's going to be the same demo. But yes, we can definitely add Pulsar examples there in this. In this. And anyway, Ozan's promised me just before this call to show you, or to demonstrate virtual thread support in Pulsar during that insight. So you will see how it works.
Spoiler. Well,
that's a spoiler. I know what.
I think it was also in the description of the
okay, so
of the insight.
I'm a pretty bad spoiler.
It will be at the end of the demo, of course. There will be a demo just now. Shall we? Do we have anything else to discuss? Maybe Clement, you want to add something?
Well, actually, so it's funny because when I started reactive messaging, so the foundation of messaging in Quarkus, we immediately started looking at Kafka and things like that, and then because Red Hat is doing a lot of work around AMQP 1.0, looking also at AMQP. So I had these two things like traditional versus streaming. And when Pulsar emerged, trying to reconcile both patterns, I was like, hey, that's cool. I even imagined that it's like an hybrid between GMS on one side and Kafka on the other side. And then you have the cloud with this horizontal scalability that you can have with Pulsar. So it's a well-designed, complete, resilient messaging stack where you can go on a spectrum from GMS use cases to Kafka or streaming use cases. So it's pretty nice to have that in your toolbox, to have a single stack. And what Matteo said is really nice, the multi-tenancy. How many times I got question about, oh yeah, we have one user that has 24 Kafka clusters, and obviously they need to exchange data between clusters, and it's a mess because, well, you need to have specific application taking from one side going to the other one. Here with multi-tenancy, it makes things so much simpler. You have a single cluster with all your app, all your teams in a single one. That's simplified a lot of things.
And there's also
I've seen more than 24.
There is also geo-replication, which is also a nice Pulsar feature too, especially in a hybrid cloud world where you can say, hey, these topics need to be replicated in 3 different places or such kind of things. You can do that. Doing it with the other stacks is generally possible, required additional tools, and can be pretty expensive. I actually didn't look at how Pulsar is doing it, so I don't know if it's expensive or not. But for the others, I've tried, and yeah, it's expensive.
I mean, it's expensive.
In terms of bandwidth.
Cloud providing bandwidth can be expensive sometimes, but that's the only price. I want to also call out one other thing about the geo replication, which is that we can also support migrating, not just migrating, but basically syncing subscription state from one cluster to another. So basically, like you can consume from cluster A, and if cluster A goes down completely, you can just move to cluster B and you can resume from where you were. There's a small amount. That's
so disaster recovery or multi-cloud with a FinOps ID behind, like, oh yeah, that cluster is too expensive. We don't have enough users to justify it. Let's move everything to another one. All these are built in Pulsar. If you, with the other stack, you need to build everything. And for example, with Ozan, we have added a lot of feature on top of Kafka. It's not simple. Sometimes it's complicated. It's yeah.
Well, now that we have Matteo online, I would like to ask something else around the operational costs and operational ease of Pulsar in general. Because, there's 2 topics. One is operational ease and the costs around operating a Pulsar cluster. And the cost aspect also touches these recent discussions around, Kafka is so expensive to operate. Again, the network costs are too much. And maybe you've heard that recent project called, it's a product actually, Warp Stream, which tries to which implements the Kafka API, Kafka protocol on top of S3. So your topics directly write to the storage, and they claim that the operational costs are like 10 times less. Do you have any benchmarks or like ideas about how the operational costs are, like how operational costs change with Pulsar compared to Kafka, let's say?
And that's the benchmark where there are things right. And we also do that too. There is that there are different conditions, right? And if you just like, you cannot detach like cost consideration for one particular use case, because it's varies widely. And one thing that I saw along this year is that in like most of the most critical use cases were not huge amounts of throughput. If you look at like like OLTP to more analytical, amount of data is lower on the compared to the analytics ones. Just because there's a bunch of logs, the amount of logs and the volume of this is huge. But if you look at the critical events, like microservices interacting, okay, that there's a new account, or I'm trying to buy something, and I'm changing the inventory for something. These are the critical ones, right? And in there, I don't think that's the cost on the right? Dominant factor.
Did we lose?
Yeah, I was just thinking.
yeah.
I think the network gremlins, they were
We have
attacking.
you few
Yeah,
seconds
well, we
ago,
lost you
or-
for a few seconds.
Okay, yeah, it was just like summarizing that is just mostly on that. What is the dominant factor typically is the how stable is your system, how resilient, what's your availability, and similar things, right? And the developer productivity, because these are the most critical factor, more than the cost on the network and disk resources, because that becomes lower and lower. But the going on the different architects, so we actually been the first messaging system that have been doing tier storage. So we've been doing S3 from 2018 that we added tier storage in Pulsar, right? So we're aware of the implication of cost for like long-term retention, right? Yes, it does not make sense to keep our storage nodes with disks mounted in either EBS or local volumes or whatever it is, with a server running and CPU resources just for keeping a disk online, right? If the data is unlikely to be read anytime soon. So offloading to S3, of course, just reduces that cost, and we can have a very long-term storage. Now, the tricky part with S3 is that it's really an object storage, right? You cannot just add data to an S3 object and have this data visible immediately. The way it works is that you create an object, you do append, and in the meantime, this data is not visible, right? Until you do close on that object. Now the data is visible. But you cannot create millions and millions of these objects, so these objects have to be big. So now you have two choices, right? Either you don't acknowledge to your producer and pose one big object, right? That's one option. But that means that your latency when you're publishing is not 5 milliseconds. Now it is 10 seconds, or I don't know, 30 seconds, 1 minute, whatever time it takes, right? Or more, right? It can be like because this object has to be big, or that you acknowledge immediately and then you can use data, right? Which is a second option. And third option is that, okay, maybe I can write locally and then I will immediately flush on S3. Now, if you just write locally on one single node and then you flush to S3, now you have a problem that you have the data is in one single node before it is written to S3. So either you have a window of where your data has a repeat factor of 1, means that you lose one server, you lose data, or that you still have to have your replication mechanism. And that means that all the traffic has to be replicated across multiple nodes, even for this temporal buffer before you can write to S3. If you look at the cost that this system have, typically is right now the dominant factor is around cross AZ traffic. Even more than the disk. Like each time you cross an availability zone boundary, it is 1 cent per gigabyte, if I'm not mistaken. Depending on how many copies you write, so it seems very low, but it's a huge amount of cost. So my point there is that I don't think that you can change the dramatic effort. You can't get out of these constraints, right? Either you defer, you have huge latency, or you lose data, or you have some form of replication which we have the same cost structure. I guess I don't know. I took a brief look, but a few months ago, but I don't remember exactly what their solution to that is. But I don't think you can get that, right?
We've got a question about whether for a small on-premise site with no Kubernetes but Docker Swarm, would Pulsar be a good choice? I saw the deployment seems more complex than with Kafka Craft.
That's an interesting one, because that a feeling I had at some point. Like, oh yeah, but with Craft I don't need a bookkeeper. Or no, with Pulsar I need bookkeeper. So yeah, that's an interesting one.
Okay, we have a solution for the Zookeeper problem, but it's very different from where Kafka has gone. In my view, the thing with the Kafka and Kraft has been that they kind of like taken the same architecture of Zookeeper and they moved it from one place to another. Basically, okay, now you don't have Zookeeper anymore, but the same logic, the same architecture has been pushed to the Kafka brokers, and the same complexity. So it's not the complexity went away; the complexity is still there because there's still a component doing that job. It is just that it changed place, and now your brokers, your brokers 0, 1, and 2, now they have a special meaning. They're also like the initial set of the ensemble. So I don't think it changed a lot. It just, I mean, yes, you have less pods, I guess, but the same problems.
You mentioned it. It fixed the Zookeeper problem. The people are fearing Zookeeper because of a long history of issues with Zookeeper.
I mean, I put into production the second cluster with Zookeeper in Yahoo. So I know like all the early Zookeeper pains and the later Zookeeper pains. So I've been using Zookeeper for 13 years now. So I know them. So the way we've gone around this has been that let's not try to do the same thing, because I don't think it is the right answer there. But instead, let's try to design to really think what do we need for what do we use Zookeeper for right now, and what are our limitations. So essentially two things. One is coordination, basically like service discovery, or like propagating things across the different nodes, or like leader election and so on, right? And also for metadata, meaning okay, where the data for this topic is stored on, and so on. This part can be quite huge. So our problem is typically that we exceed the capacity of Zookeeper, because if you have 1 million topic, now you have several gigabytes of metadata, and Zookeeper just blows up. so we went a different route. So we started a new service which is called Oxia, which we open source earlier this year, and it's a new service. It's written in Go, and it's kind of like doing a coordination and metadata, but in a scalable way. So basically, the data set is partitioned. There are namespaces, and you can add more pods and have more capacity. Basically the gist of it is that instead of thinking of like bare metal as the environment, as the minimum environment, like it was with Zookeeper and Craft in a way, we kind of so yeah, people say less components are good, but instead of like assuming bare metal as an environment, we assume Kubernetes as the environment, and that basically gives us much more freedom to have a much easier implementation of the replication protocol. Because of that, we can have all this auto scaling, and we can have horizontal large capacity of metadata, and we're not boxed in. So yeah, it's a different service. So it's a set of pods, but I think in the long term it is a better choice, because it's kind of like it's a different component, and with the different scope. So cramming everything into the brokers seems to just hiding the problem in a way.
I see. And in Pulsar, you can just swap the Zookeeper metadata store implementation with the Oxia.
Yes.
Okay.
So having promised a demo, we should probably get onto the demo so that we've got time for it, and so that people can sort of put sort of visualize what we're talking about.
So Holly, you can share my screen.
Cool. I think if I share it now, we will get the infinity mirror. So
let me.
Okay, so we've still got the infinity mirror.
Is it okay now?
Yeah. Okay. Cool. There we go.
Okay. So the demo for today is taking the quick start application that we introduced maybe more or less 2 years ago for Kafka, and we actually, when we rolled out the Pulsar integration, we took the same exact quick start application and ported to Pulsar. And I'm going to start with that quick start application and introduce a bit how these concepts that we just discussed for Pulsar actually integrate with Quarkus and how we can use that already. So the application is, I'm going to use our blog, the guide. So this is the quick start guide for Pulsar, if you're interested to take a look. And the application is pretty simple. Instead of one application, we have two. We have the code producer and the code processor. And the code producer has a web interface, and it has a REST endpoint. And when there's a HTTP post to that code request endpoint, it will push. Oh, this is Kafka, but yeah, it should be in Pulsar. Sorry about that. It pushes a code request to a Pulsar topic, and that request is picked up by another application that is consuming that topic, and it generates a code, a random code, and pushes back to a code topic, and the code is then consumed back in the producer and sent as a service sent event back to the client. The interesting thing is this topic is a string-based topic, so the schema is string, but the code is a composed object of the code ID and the price. So we will see how all that integrates. Let me maybe first run the code and see, show you the web interface. And for those who have already checked out the Kafka Quick Start, it is the same application. So now that I'm running the Quarkus dev mode, one thing that you will notice is that the dev service is already there with Pulsar. So we have, when you run the dev mode with the Pulsar extension for Quarkus, you will have a service that is started for you, having a standalone mode Pulsar node. So that's already started, and we will see that that's exposed to a random port in my machine. Let me start the second application as well, which will automatically discover this service and bind that to and use it as a Pulsar client.
By service, you mean the dev service? Or the
Yes, I'm using this dev service.
Pulsar broker.
Exactly. So that's the
which is to just mention, because it was mentioned in the chat. It's a one image containing everything, so you don't have to have multiple components in that.
Exactly. So that this is the standalone mode
Yes.
Pulsar image that's created, and this is the official image. I think it is still on the 3.0, and there's a 3.1 also, and you can easily swap that with the configuration. And let's see if the whole system works. We are recursing codes, and the processor is actually generating random codes and sent back to the producer. What we can see is, let's have a look at the code. And the codes resource class is the producer. So I'm getting a post request in an add point. I'm using the emitter from the reactive messaging framework to basically emit events to a channel. And channel is the building block for the reactive messaging. And you see that same primitive in Kafka extension and Pulsar extension and AMQP and RaveTimeQ. It's always the same ones. And of course, the implementation, the connector underneath changes significantly. But when you set up the marshalling on marshalling, it is more or less transparent to the developer. So we are using the emitter. We declare the channel with its unique name, and when we get a post request, it will be sent to that channel, which is to that channel called code requests. And by default, it's bind to a topic with the same name. If you go to the properties, well, actually, this time I've overridden the topic, which shows that you have different. The Pulsar topics are actually a complete URI with type of the topic, persistent or non-persistent. Correct me, Matteo. Tenants and namespace, right? Exactly. So then this topic is listened by the second application, which is the code processor. So it is deployed separately. This time I've named the channel more easily requests, and the request as an ID is consumed by this method, which is annotated with incoming and outgoing. So this method will be called each time there's a message consumed by Pulsar from that topic. Let's see if the topic is, so in the configuration, the topic is the same one, the code requests. Because it's a string implementation, I mean, the message type is string. it is automatically discovered by the Pulsar extension, and the schema is set to string. So you don't need to do anything for the schema in this case. And what we do is simply generate a random int and construct the code, which is a really simple bean of ID and price, and send back to return back from my method, which is again annotated with outgoing. So it will be sent to the outgoing channel, which is named codes, to the codes topic. In this case, because it's a complex type, by default we use the JSON type for complex types. In the case for the producer application, it will be consumed in here with this again the channel annotation here, which will inject a mutiny reactive streams implementation, which we can easily chain that to a server sends events by simply returning it, and now I am logging it. It is a bit tricky to understand that Pulsar actually requires a schema for every topic by default. So we are playing well with it in the sense that if you have a complex type, we generate a JSON schema by default, and it is automatically cabled to your channel. So that's why in this application, the producer one, we don't have to do anything for the configuration. It has been already detected. If we go back to the logs, we can see that we have created a consumer for codes channel with the schema of JSON schema. But as an example,
one thing about that is with Kafka, again, you need to have a schema registry, or at least it's heavily recommended, because schemaless is great when you have an hello world, but as soon as you need to scale up, it doesn't really work. You need to understand the language between all your entities. Pulsar, again, built in, it's just there.
Yeah.
So what we do to simplify the developer experience to say, well, 99% of the case, maybe less, 90% of the case, you are going to use JSON because we want something readable. So let's have Quarkus generate that for you, and then you get your thing, and it's inside it's registered, the schema is registered, and that's exactly why we are doing that.
And we also detect that if the complex type is a arrow generated type, we use the arrow schema. If it's a protobuf type, we use the protobuf schema. So the auto configuration there is highly efficient, I think. But again, we do a second thing on top, which is in some cases maybe you don't want to validate the schema or use the JSON built-in JSON schema. In those cases, we do propose a utility to generate an object mapper, so Jackson schema for a given type. So this is by configuration, and in this case, this is the processor application which does that. So now that we have the schema and the basic configuration out, what we can do is just write some code and try to change things a bit. Let me see if I can maybe log that, start by logging it in the processor also. So the price for requests is...
See, Oli, Ozan is seeing your tweet and is using the new log API.
Yeah, that's a shout out to Ladislav. I think that's great. We don't always need to see the log implementation that's underneath. Code requests and price. So let's see if that changed our application. Oh, sorry about that. Yeah. Now that I have to see that has been demo effect. Oh, formatting error, of course. That's this S. And we see that the application kept on working and kept on logging the price. The next thing that I want to show is we've discussed different topologies for consumers and producers. Let's then create a second producer for the processor part. So we can spin another an application for dev mode, in this case for processor, and see how Pulsar reacts to that.
So one word of question here. Generally, don't start twice the same dev mode in two different terminals from the same directory. This is not a great idea.
Yeah.
But
no,
What could possibly go wrong?
this error actually is expected. That's what I wanted to show. In this case, Pulsar actually checks that a producer is writing to a topic, and this is this instance, and rejects the second producer with the same name. Again, to ease things up, we choose the producer name as the channel name, but this can be changed easily. Now for that, for my processor application, I will use, again, for the outgoing type, so for codes, this is my producer. I will change the producer name to a generated type. So I want the Quarkus application to generate that for me. And now, if we refresh things up, both applications have started, and let's see how the codes keep coming. The one thing that we will notice is that because I have two processors, I will have 2 times the processing and 2 times the price that is sent back to the producer. This is because the subscription by default is exclusive, and it will just take the messages one by one from each processor, and won't check anything if multiple producers are publishing to the topic. The way we can change that is we can go ahead and let's see, messaging, incoming requests, and have a subscription name for my requests topic. I will do that as again as a calculated property. This time Quarkus. I'll choose that Quarkus application name, and I will also say that this subscription is a type of failover. So subscription type is failover. In this case, we will see that so the request topic that is subscribed by these 2 processor applications will actually choose one processor over the other. Let's see. I will generate requests again. The error was also interested in here, I think. Let's see if we can check that, or maybe not. Requests, not request. But that's an interesting error as well. Yeah. So in this case, the failover works because it choose one processor over the other. And if I actually stop this one and keep producing events, the second one will take over. Another thing that we can do is switch the failover to shared. So this will, on the subscription level, apply a round robin, basically. So the messages will go, let me see. So it restarted my processor because it detected a change of configuration. I will start the other one. Yeah. And the messages are, the codes are sent only once, and the code requests are actually shared between the two processors. Another interesting one is the key shared. So this is basically the Kafka equivalent of keyed partitions. So the subscription will choose, will assign a key to each of the subscribers, each of the consumers. And for that to work, of course, we need to be publishing events with a key. So I'll go back to my producer and change that code. Instead of publishing just the payload, I can, with reactive messaging, I can say, I'm going to construct a Pulsar message of payload. But I also want to add a key. I can add more complex types with the metadata, and but in this time we are just using the key. So actually, what I'm going to do is construct a key. Let's see. I'll get the hash code. Let's see if we do that. I think we'll have a more or less a coherent keying for this thing. No, not this one. Yes, well, I'm using 3 times the UID dot toString, but that's okay. So if you go back to our application, again, the code has changed. The dev mode has restarted, and we can also see that the keys are taken into account in my processor. Yeah.
Sorry. One small addition here is that, so in Kafka you only do that per partition, but with key share, basically you can have as many consumer on a single partition as well. So
That's
you can
true.
have partitions, and then even within a partition you can have end consumers, and a single key will go to the same consumer always.
Yeah. Your key space is not restricted to the number of partitions you have.
Yeah,
Yes.
because
So
you
can,
don't necessarily have partitions here, so it's really
That's true.
the key which is associated to the consumer.
That's true. Yeah.
But if your key space is more, like 4 different keys, then having more consumer won't help. But generally, it's not the case. But yeah.
One difference also for Pulsar key mechanism is that keys are always strings, I think. Correct me?
Yes.
Yeah. You can also get them as bytes, but the default, keys are only strings, which I think is a useful simplification.
Yeah. Well, in Kafka, your keys can be any types, but seriously, 99% of the time, it's a string.
So
or can serialize the string anyway, right? In the end, it's all bytes. So
that's
even
true.
if you have some binary string, you can base 64 it, and then that's it.
Yeah. Yeah. So in order to consume the keyed message, instead of consuming only the payload, so we had the string, I'm going to consume the message instead. So the message, again, an important point here, the message type also exists in reactive messaging as a primitive. In here, we are using the Pulsar message. So each message in Pulsar comes wrapped in a message interface. In this case, I'm going to get the value from the message, and also the code request key. And here, again, the value. Now we should be able to see the keys that are distributed among the two processors. Oh, sorry. So the one on the right is also only getting -1. The other one is getting the 0 and the 1. I think we can stop there for the for different types of subscriptions. You can check out, of course, the Kafka reference guide, but also the Pulsar documentation for an in-depth description of different types of subscriptions. What we can check out next is some like failure management strategies, because Pulsar already comes with a couple of ones that are pretty useful. Let's say that in my processor, I want to only respond the code to if the price that I generated is an even one. Very simplistic check in a meaningful way. Let's see if the price that I generated is even. Price can I even for requests, and we get the code request value. So basically, this is a deliberate error case, because basically, if we try this message, maybe we will generate a one that is not even, and it will pass. So let's see. In here, we see that some requests are impending because the processing actually failed with price cannot be even. Pulsar clients, consumers come with a by default redelivery mechanism, and in Quarkus integration, we automatically negatively act, so NAC the message that produced an error for its processing. And when the message is NAC'd, Pulsar client actually by default redelivers the message with a certain delay. So this is configurable in. I need to be remembering the negative ACK redelivery delay macros. I will just say a few words about these configuration names. These are the configurations that are given to the Pulsar clients, Pulsar consumer, and Pulsar producers that are created underneath. And the names are a bit strange because these are directly passed to the configuration objects that Pulsar clients receive, and we will just see now that there are different ways of configuring, because again, Pulsar clients have lots of features built inside, and because of that, the configuration can be a bit complex as well. So now, what I just
one important thing is that all the entries are passed to the Pulsar consumer. So if you use the next version of Pulsar and there is a new property, you can pass it without in Quarkus having to add anything. So
exactly. And we actually merge different kinds of configuration options together to pass to the Pulsar client.
So Ozan, it's already the top of the hour. So
yes,
conclude.
Maybe what can we say lastly? Oh, we promised the virtual thread support, right? So let's give that.
Well, or we teased it very well for the commit tomorrow where we will add the example.
So basically, the virtual thread support has an annotation associated with it, and in reactive messaging and a bunch of different extensions with Quarkus support this annotation run on virtual thread. So for messaging extensions, instead of your blocking or like your non-blocking processing, swap it out with run on virtual threads, and just make sure that you are running on Java 21, which is not the case. Use 21, and normally it should work without any hiccups. And if your runtime is not 21 or doesn't support virtual threads in general, it will fall back to the regular worker pool. Again, we see that the thread that is executing the processor is a Quarkus virtual thread, and we can go beyond if we have a couple of minutes. If we generate a bunch of requests, let's see, outgoing in my producer application.
How are you doing, Clement and Matteo? Do you have a few minutes extra?
Yep.
Cool. I love that we left virtual threads to the last 30 seconds of the demo,
Yes.
and it still just went in and worked.
So basically what I'm doing is generating a bunch of requests. So this method will be called like in a loop by reactive messaging to push events.
Literally an infinite number of times.
Exactly.
Again, don't do that in production, please.
Well, yeah. Let's see.
The specs mandate to support such kind of case, but I'm like, okay.
Yeah, let me modify the. I think it should work out of the box because it's a merge. Oh yeah. Didn't we auto detect that?
We could. We already indicate this, so we could we could do that for you. Yes. The question is, do you really want to do that, or?
And let's see if we can remove the error case. And all of these, well, we see that a bunch of virtual threads created per message. And let me maybe atomic integer print out the parallelism for our method. So I'll get incremented in here. Well, we have, let's increase a bit the thread.sleep, and in here parallel s.
It's essentially the level of concurrency, but fine.
Yes, yeah, level of concurrency, exactly. Decommenting it, get an increment.
Yep.
Yeah. Let's see if that. So yeah, exactly. If I can maybe.
Yeah, it's
close
there.
that.
So you should reach 1024 at some
Maximum,
point.
yeah.
Because we have that as a constant in as a constant, as a configurable
As a
option in write to messaging to avoid getting out of memory. Because basically, if Pulsars, if you send millions of messages per second and you have virtual thread and you don't have any concurrency limit, it will just poll and create virtual threads, and you will run out of memory. So to avoid that, we have a concurrency limiter set to 1024 by default. It's obviously configurable depending, so you can tune it depending on your memory and everything. But yeah, basically right now we are processing more than 1024 messages concurrently,
yeah.
on threads. So every message gets its own virtual thread.
So each message that arrives in here will be entering this method in a new virtual thread. What I wanted to show again was a bit more of the different failure mechanisms. Again, the dead letter queue that we mentioned, it's pretty easy to set up with Pulsar. Some keyed processing is easy as well. But I think we made a good tour of different options. And if you want to check more, there's of course the Quarkus guide for Pulsar. Let's see. So it's basically guides / Pulsar, which gives an in-depth description of how different features work, and the quick start, which is this application that you can code step by step. Of course, I think one thing that I should mention is that Pulsar documentation is very in-depth and well described. Like a bunch of features are very well described in the Pulsar documentation as well. So if you want to check out that. Anything to add, or are we are already overboarded it?
We got two. Well, the last question.
Holly, you muted.
Oh, thank you. Yeah, sorry, let me rewind. So we had one final question, which was, can you apply that flag as well in this sample? And I think I was too slow to bring it up, so I'm not 100% sure which flag it was, but maybe you know, Ozan. And can that be done for multiple separate virtual thread pools, and can that be referenced in the annotation?
So the last one is very interesting because it's a debate, but multiple virtual thread should not be pulled. So that's the first thing. The JEP clearly said don't pull them. There are things that you used and killed, and that's it. Having several virtual thread pool has also a second nasty thing, is that it's actually creating more fork join for your carrier thread behind the scene, which means that you are overcommitting on your CPU, which is always a bad thing. I don't really explain this particular point, but I explain why it's a problem on how it's working behind the scene on our blog. And let me find the here is a link, so if you can share it. So where I explain how virtual thread works, why the integration is done like that, and why we should not pull them and having multiple pull. The only thing that can be a use case. One thing that we could imagine is giving different names, different name patterns when we use that. But basically, it will be the same pool, just with different multiple facades setting the name. But yeah.
Yeah, I'm reading the question. Excuse me.
That has stumped the
Yeah.
Well, maybe open a discussion on Quarkus.io. Well, on the
Zulip.
discussions. Yeah, or no, well, or either on Zulip or on the GitHub discussions from Quarkus, and then we can answer. But yeah, it's going to be hard to answer there.
I think his question is just that he has multiples, producers and consumers, that he wants to get from in a simulation, and just how does he coordinate that with multiple threads? That's virtual threads, but that's my. So if he has to read and push, or read and handle the messaging, will that be something he does in one thread, or can he do it in multiple threads?
It's going to use multiple threads, but we still have flow control, so we will never flood the system. So the outbound side will dictate the pace. So if you write to a database, for example, it's going to be slightly slower because you can't write as fast as you can generate UIDs.
Yeah. Exactly. Yeah. In this example, there's virtually no boundary for concurrency because we are just doing a thread.sleep, right?
Yeah, but if we would have written in a database, you will see that it will not create so many virtual threads because your control, well, your limiter will be your database.
And we've got the follow-on as well, which is we have a secure access service edge product for which we have a simulator where we have multiple device instances in the runtime.
If it's in the same runtime, it can use the same virtual thread. I mean, virtual thread executor.
Yep.
Yeah,
it's important to understand that they are not pooled, so we can create them. We can create as many as we want.
Yeah.
There's no
and the same annotation. I mean, if you annotate your different producers or different methods with run on virtual threads, they will still run in the same fork join pool as virtual threads.
On the same pool of carrier thread, but
exactly.
on different virtual threads.
Cool. Well, thank you very much. Yeah, lots of good questions, and thanks for staying the extra 10 minutes to finish up the demo and the extra questions. And with that, I think we're done, unless there's any sort of final closing thoughts.
I'm good.
Thank you.
Yeah, excellent. Thank you, everybody.
Thank you.
Cool.